Climate change is raising temperatures almost everywhere on the planet at once, which raises an obvious and genuinely frightening question. Could drought rise everywhere at once, too? Some earlier research suggested it could, estimating that as much as 1/6 of the planet's entire land surface could slip into drought simultaneously, a scenario that would be catastrophic for global food systems and economies. A team of researchers just spent years digging through 120 years of climate records to test that possibility directly. What they found is that something has been quietly preventing exactly that scenario from happening for over a century, and most people have never heard of it. The research, led by scientists at the Indian Institute of Technology, Gandhinagar, working with international collaborators, analyzed global climate data stretching all the way back to 1901 through 2020, a full 120 years of records. Their goal was to directly measure how often droughts actually synchronize across the planet, meaning how often large portions of different continents dry out at the same time rather than independently. What they found sharply contradicted the more alarming earlier estimates. Across that entire 120-year record, synchronized droughts, meaning drought conditions striking multiple major regions simultaneously, only ever affected between 1.8 and 6.5% of the planet's total land area at any given time. That's dramatically lower than the 1/6 figure, roughly 16 to 17%, that some earlier research had raised as a plausible worst-case scenario. The study was published in the journal Communications, Earth, and Environment. The explanation the researchers landed on comes down to something happening in the world's oceans, specifically shifting sea surface temperature patterns that act as a kind of natural brake on how uniformly drought can spread across the globe. The most significant driver behind this effect is a climate pattern most people have at least heard of without fully understanding its global reach, the El Niño Southern Oscillation, the same Pacific Ocean cycle currently making headlines as a strong El Niño develops this year. During El Niño years, when the central and eastern Pacific runs unusually warm, Australia tends to emerge as a major drought hub, while other regions of the world respond in completely different, sometimes opposite ways. During La Niña, the cooler counterpart phase, the drought pattern shifts again, typically spreading out more broadly across different regions rather than concentrating heavily in any single area. According to the study's co-author, Danish Mansour Tantri, these ocean-driven swings create a patchwork of regional responses. And that patchwork is precisely what limits the emergence of a single, global drought covering many continents simultaneously. It genuinely helps to picture this mechanism visually. Imagine drought risk as a spotlight that can only illuminate one region of the world at a time, rather than a floodlight capable of covering the entire planet simultaneously. As ocean temperature patterns shift, that spotlight moves. Australia one year, parts of Africa or South America in another, depending on exactly how the Pacific and other ocean basins are behaving at that moment. Because the spotlight is constantly moving rather than expanding to cover everywhere at once, the worst drought conditions tend to stay geographically contained rather than compounding into a single planet-wide catastrophe. This isn't a passive absence of drought risk, it's an active, ongoing redistribution of where that risk concentrates, driven by ocean physics operating on a genuinely massive scale. It helps to understand exactly how researchers define and measure drought in a study working across a full century of global records, since drought itself isn't a single, universally agreed upon threshold the way a temperature reading is. Climate scientists typically rely on standardized indices that compare actual precipitation and soil moisture against the long-term historical average for a specific region, allowing conditions in a naturally arid region and a naturally wet region to be compared on the same relative scale. A region is generally classified as experiencing drought when conditions fall meaningfully below that region's own historical baseline for a sustained period, rather than using a single fixed rainfall number that would mean something completely different in the Sahara than it would in the Amazon. Building a data set capable of tracking this consistently across the entire planet, across every major climate zone for 120 consecutive years, represents a genuinely enormous undertaking, combining historical rainfall records, tree ring data, and other proxy indicators for the earliest decades of the study period before modern satellite and sensor networks existed. It's worth grounding this in real historical examples, because synchronized versus regional drought isn't just an abstract statistical distinction. It is played out in specific, documented events throughout the very century this study examined. The Dust Bowl of the 1930s devastated the American Great Plains through a combination of severe regional drought and poor agricultural practices, but it remained substantially a North American event rather than a globally synchronized one. Major droughts throughout the 20th and early 21st centuries have repeatedly followed this same regional pattern. Severe, sometimes catastrophic conditions concentrated in specific parts of the world, while other major agricultural regions elsewhere continued operating under normal or even favorable conditions during the same years. That pattern of regional concentration rather than global simultaneity is exactly what this new research quantifies precisely for the first time across the full 120-year record, rather than relying on scattered historical anecdotes from individual events. If you want to understand how this connects to what's happening in the world right now, this same ocean mechanism is actively relevant given the strong El Niño currently developing in the Pacific. A like and a subscribe genuinely helps more people see research like this broken down clearly. And this is exactly the kind of long-term climate pattern worth continuing to track as conditions develop through the rest of this year. This research carries real, direct implications for global food security. Because the study didn't stop at drought patterns alone, it also examined historical crop yield data for 4 of the world's most critical staple crops: wheat, rice, maize, and soybean. When moderate drought conditions struck a given region historically, the researchers found measurable, significant impacts on yields for these crops in the affected area. That finding matters enormously for understanding the actual stakes here. If ocean temperature patterns were not providing this natural braking effect, and droughts genuinely could synchronize across major agricultural regions simultaneously, the global food security implications would be severe, potentially straining supply chains and food prices across multiple major producing regions at the exact same time, rather than allowing global agricultural systems to absorb a regional shortfall by drawing more heavily on unaffected regions elsewhere. It's worth being precise and careful about exactly what this research does and doesn't mean, because getting this distinction right separates an accurate, useful story from something that could be badly misread. This finding is not evidence that drought risk overall is declining or that climate change isn't increasing drought severity in specific regions. The researchers are explicit that drought risk is real and rising in many parts of the world as global temperatures climb. What this study specifically addresses is a narrower, more particular question: whether that rising drought risk tends to hit the entire planet simultaneously in perfect unison, or whether it continues playing out as a shifting regional patchwork the way it has for the past 120 years. The answer, at least based on this century plus of historical data, is clearly the latter. Ocean temperature patterns act as a natural disruptor, specifically against the kind of uniform, globally synchronized drought that would be almost impossible for the world's food systems to absorb without eliminating regional drought risk itself, which remains a serious and growing concern in the specific areas it strikes. This mechanism also connects directly to why the strengthening El Niño event currently developing in the Pacific matters so much for global agricultural monitoring in the months ahead. As that event continues intensifying toward what multiple forecasting centers now expect could become a strong or even super El Niño by winter, the historical pattern documented in this study suggests Australia in particular faces an elevated drought risk during this specific phase of the cycle, a pattern that has repeated consistently across the ocean temperature record researchers examined. Understanding that this represents a redistribution of risk into a specific, well-documented regional pattern, rather than a sign that global synchronized drought conditions are forming, gives a considerably more accurate picture of what to actually expect and monitor as this El Niño event continues developing. It's also worth understanding that the Pacific's El Niño Southern Oscillation isn't the only ocean pattern contributing to this braking effect, even though it's the most well-known. Researchers studying related climate mechanisms have also pointed to the Indian Ocean Dipole, a similar temperature seesaw pattern playing out across the Indian Ocean rather than the Pacific, as a significant independent contributor to drought variability in regions, including the Middle East and parts of the Mediterranean. A separate 2026 study specifically examining winter dry spells across the Levant region found that Indian Ocean temperature patterns played a measurable role in that region's drought variability, largely independent of what the Pacific was doing at the same time. That's an important detail for understanding the full picture. Multiple ocean basins, not just the Pacific alone, appear to be contributing their own independent, shifting influences on regional drought patterns, and the combined effect of all of these systems moving somewhat independently of one another is part of why a single, globally synchronized drought event has remained so rare across the historical record. The odds of every major ocean basin pushing drought risk toward the same regions at the same time are considerably lower than any single basin doing so on its own. There's also a broader scientific value to this kind of long-term pattern research that's worth appreciating on its own. A single year, or even a single decade, of climate data can make almost any pattern look alarming or reassuring, depending on which specific window you happen to examine. Drawing on a full 120 years of consistent records is what allowed these researchers to distinguish a genuine, physically grounded pattern. Ocean temperatures reliably redistributing drought risk rather than allowing it to compound globally, from what might otherwise look like coincidental regional variation if you were only looking at a handful of recent years. That's precisely the kind of long-horizon data that gives a finding like this real statistical weight, rather than resting on a small, potentially unrepresentative sample of recent climate behavior. This finding also opens up a genuinely practical application beyond simply improving scientific understanding of drought risk. If ocean temperature patterns reliably create predictable regional drought hubs rather than random, unpredictable global variation, the predictability becomes a genuinely useful early warning tool for agricultural planning. Once a strong El Niño or La Niña pattern is confirmed developing, as one currently is in the Pacific, agricultural forecasters and food security researchers can look to this same historical pattern to anticipate which specific regions face elevated drought risk months in advance, rather than waiting for drought conditions to already be underway before responding. This is exactly the kind of application seasonal climate forecasting has been working toward for decades, using well-documented ocean-atmosphere relationships to provide meaningful lead time for farmers, water resource managers, and international food security organizations to prepare for regional shortfalls before they fully materialize. The 120 years of data underlying this study essentially provides a much stronger statistical foundation for exactly that kind of forecasting, showing not just that these regional patterns exist, but how consistently they've repeated across more than a century of observed climate behavior. None of this changes the reality facing any specific region currently experiencing serious drought conditions right now. A regional drought hub, wherever the shifting pattern happens to concentrate in a given year, still represents a genuine, serious hazard for the communities, farmers, and ecosystems located there, regardless of whether the rest of the planet happens to be drying out at the same moment or not. What this research adds is a clearer, more accurate picture of the planet's overall risk profile. The worst case, globally synchronized drought scenario that some earlier estimates raised as a plausible outcome appears considerably less likely than previously feared, precisely because of a natural ocean mechanism that has been quietly operating throughout the entire 120-year historical record these researchers examined, mostly without public awareness that it exists at all. Understanding this mechanism doesn't eliminate the real rising drought risk climate change continues to drive in specific regions around the world, but it does replace one of the more frightening theoretical worst-case scenarios with a clearer, evidence-based picture of how drought risk actually distributes itself across the planet, rooted in over a century of consistent historical data rather than a shorter-term projection. Thank you for watching, and I'll see you in the next one.